Welcome to the second lecture of the course Mathematical Finance. And this week we are going to talk about Ito calculus, Brownian motion, and stochastic integration. And we're going to give a first derivation of the Black-Scholes, the famous Black-Scholes partial differential equation and the Black-Scholes option pricing formula. So what is Brownian motion? Brownian motion is a stochastic process. It's kind of a mathematically abstract stochastic process. And Brownian motion is also called a Wiener process. So this is the reason for using the letter capital W to denote Brownian motion. And it has the following property. Brownian motion starts at 0 at time 0. And then if we consider an increment of the stochastic process from time t to time t plus delta t. So this increment is kind of the value at time t plus delta t minus the starting value at wt. All those increments are statistically independent from each other. And this is, and any change that has happened in the past basically says nothing, has no correlation about what's going to happen in the future. And then the third property is that each increment has a normal distribution with mean 0 and variance equal to the step size. So the standard deviation scales with square root of delta t, but the variance scales linearly with time. And the final point or definition of Brownian motion is that each path of the Brownian motion stochastic process is continuous, but it turns out that the path is extremely wiggly, so it is continuous everywhere, but nowhere differentiable. So if you look at the path as kind of a plot of time, it's a pretty wild function that is continuous everywhere, but differentiable nowhere. And we're going to talk about this a lot later, but the Brownian motion is kind of the archetypical example of a stochastic process, which is known as a martingale. And that's due to these independent increments, and each increment has mean 0. So that means that the expectation of the process at a later time point is basically the value where the process is now. So on average, we are not going up or going down because each increment has mean 0. So the Brownian motion path, as I said, is a pretty wild function. So it is continuous everywhere, but nowhere differentiable. So this is kind of a nice animation. So if you keep on zooming into this Brownian path, you basically keep seeing the same structure. So it is continuous, but it's let's say infinitely wiggly everywhere. And basically we can derive this already from the definition. So if it is kind of has a normal distribution with a variance equal to the time step, if I try to take a derivative, so I could look at the differential at w at time t plus u minus wt minus u, then this thing, because I have just have this Brownian increment, has a distribution which is a normal distribution, which has variance u, but because I'm scaling it with also a factor of u, I need to pre-multiply with this factor squared. So I get that this differential for a finite time step, so for a finite time step, this is a well-defined thing. This differential has also a normal distribution with mean 0, but with variance equal to 1 over the length of the time step. And then we see that we get into trouble or strange behavior. If we now let u approach 0 from above, then this distribution basically is not well defined or kind of explodes into something that physicists call a white noise process, which is kind of the limiting process of a normal distribution with mean 0 and infinite variance. And this infinite variance is kind of, let's say, the representation of the infinite wiggliness. So we really cannot define a derivative because a derivative is kind of flying all over the place and even so badly that this derivative process has infinite variance. However, the path itself is continuous because the increment is a normal distribution with mean 0 and variance delta t. So if I let delta t become smaller and smaller, I basically have a normal distribution that collapses into a certain thing with value 0. So the path is continuous everywhere, because if I make a very small step from wt to wt plus u, the function is continuous everywhere. So it's a pretty interesting function that is, yeah, continuous everywhere but differentiable nowhere. So that's probably a pretty wild function that you haven't really seen much before. So how do we construct this random process that kind of lives continuously in time? So the way that we can construct Brownian motion, or one of the ways, there are multiple ways of doing it, but this is kind of a nice and easy way, is to construct a binomial random walk. So what is a binomial random walk? By saying I look at discrete time steps delta t and the Brownian motion at time I plus 1 delta t is equal to the Brownian motion value at time I delta t. And then I'm doing a coin flip with probability 1/2, 1/2. And with probability 1/2, I'm going to say, I'm going to add plus square root delta t, or with probability 1/2, I'm going to add minus square root delta t. Why is this a clever choice? Well, the expected value of plus square root delta t and minus square root delta t with probability 1/2, 1/2 is exactly equal to 0. And the variance of this binomial random variable is indeed equal to delta t. So we have now, for a time step delta t, with this kind of random walk with coin flip process, we are matching the correct theoretical mean and variance of the Brownian motion for a time step delta t. And this plus or minus square root delta t, this may look familiar to you because this kind of Brownian, this random walk, binomial random walk construction is kind of, it's the same thing that we are using for constructing our binomial tree. So in the definition of u and d in the binomial tree, we were using e to the power plus sigma square root delta t and minus sigma square root delta t. So the plus square root delta t and the minus square root delta t that I've made in red here is basically the two possible realizations of this binomial coin flip variable. And what we now can do is, this is a valid definition for each positive value of delta t, and it has the correct mean and variance. So if we now take the limit for finer and finer and finer time steps, then in the limit we are converging to this continuous process that is the, let's say, continuous time limit of the Brownian motion process. The path of the Brownian motion is pretty wild. So if we take a change in Brownian motion and if we square it, then the change in the Brownian motion squared is basically equal to delta t. And we can see this from the binomial tree. So if we take a change in the Brownian motion and we square it, we get this coin flip variable. But we have probability 1/2 of going up, of having a value of +1, and probability 1/2 of having a value of -1. But if we square that, we get 1/2 times +1 squared, or 1/2 times -1 squared, which is also +1. So the quadratic variation of Brownian motion is a deterministic thing. It is basically the size of the time increment. And if you go to the definition of the Brownian motion directly, it's a bit more tricky, because this is a normal distribution with mean 0 and variance delta t. If we square a normal distribution with mean 0, we are going to get a chi-square distribution with 1 degree of freedom, but we are scaling it with delta t. So this, let's say, on a finite time step delta t, this is a random variable with mean delta t, but variance 2 times delta t squared. So there you see, but again, it's proved by hand waving here that if we let delta t go to 0, then kind of the variance is kind of collapsing to 0 faster than the mean. So we are in the limit, but it's a bit shaky. We are converging to this deterministic quantity dt. So you often see the notation that dw squared of the Brownian motion differential squared is equal to delta t. Now the next step is the idea of stochastic integration. So if I have a random process x and I have a Brownian motion w, can I give a meaning to the stochastic integral, the integral from 0 to t of the process x t integrated against these Brownian increments? And this is a pretty wild thing, because I have just argued a few slides ago that the derivative of Brownian motion, the differential of Brownian motion, was this kind of very nasty white noise, infinite variance, normally distributed process. So can we actually do this in a sensible way? And the answer is yes. And this was discovered in the 1950s by a Japanese mathematician called Ito. And the way that we work with stochastic integration is that we use Ito integration. And what do we do with Ito integration is that we take what is known as left sums. So that means that if I chop this integral into, again, in a finite number of time steps, then I'm going to evaluate for each interval from I delta t to I plus 1 delta t, I'm going to evaluate the x process, the integrand at the left point of the interval at I delta t, but the increment in the Brownian motion, I'm going to then evaluate from I delta t to I plus 1 delta t. And for economic purposes, this is the right way of modeling gains on trading or stochastic returns on trading, because what happens in the real world is I cannot predict what's going to happen with the stock prices. So if I want to invest for 1 day or for 1 minute, I can buy the shares now at time I delta t. And then I have to wait what happens with the world. So I have to wait from I delta t to I plus 1 delta t. And then only at that end of that time point, I can do something again. And that notion of kind of investing at the beginning of the interval and then kind of wait for the duration of the interval, what's happening with my stochastic stock price or with my Brownian motion, that is exactly captured by the idea of an Ito integral. So for economic modeling, and especially for kind of gains on trading and replicating portfolios, option trading strategies, Ito integration is, let's say, is the right way of modeling the stochastic returns on trading. And how do we construct a stochastic integral? Mathematically, you kind of do it in 2 steps. You first say, let's consider random variables capital X that are piecewise constant functions. For an x that is a piecewise constant function, basically we can use directly this left sum type of definition. Here I'm implicitly using equally spaced, but you can use non-equally spaced. But the clever trick to use is that you say, I first start with random variables that are piecewise constant functions. Then we can kind of define the integral as taking these left sums. And then you can take a limit argument by saying, if I have a non-simple stochastic process, I can kind of, like a Riemann sum kind of idea, I can, if I make finer and finer and finer delta t partitions, I can approximate a non-simple stochastic process as the limit for delta t going to 0 of simple functions. And then I define, like Riemann integration a little bit, I define the stochastic integral as the limit for delta t going to 0 of these kind of simple function summation integrations. It's a bit tricky to refer to Riemann integration, because with Riemann, it doesn't matter whether you evaluate the function at the left or in the middle or at the right. but because Brownian motion is so wild, it does make a difference. So in Ito integration, it is super important that you evaluate your X process at the left point of the integral. And if you evaluate it in the middle, you end up with a different type of stochastic integral. So it is, you do see that we are kind of on the edge of what is kind of possible, because the dW process is so wild and non-differentiable. It is the choice of evaluating X at the left or at the middle or at the right actually does make a, leads to a different definition and a different outcome of stochastic integration. The only type of stochastic integral we are ever going to work with is these Ito integrals with the left points. So what are properties of stochastic integrals? Is that the expected value, no matter what X is, if I'm integrating X against dW, the expected value is always equal to 0. If we have an xt that does not look into the future, and we say this mathematically, that the process x of t has to be adapted to the Brownian filtration. So basically I cannot look ahead. And again, if you think about trading, if I could look into the future, then I would know which stock I want to buy and I would get really rich, but unfortunately that's not possible. And therefore there is no systematic way of getting rich. So again, the Ito integral is kind of, has intuitively the right kind of behavior that I cannot predict. I cannot predict which stock is going to win or which investment is going to win. And again, it's basically the left point integration. So it's Ito integration that has this particular property, which is very useful for us as a model for trading. So the proof goes by the left point of X times the independent increment. So if X is evaluated at I delta t, and the Brownian increment from I to I plus 1 delta t is then independent from this term here. So the proof goes, I take the summation, then expectation is a linear operator and summation is a linear operator. So I can flip those two around. So then I can write the expectation of the sum as the sum of the expectations. And then in the second step, I'm saying I have the expectation of X times the Brownian increment, but X is evaluated at the left point and the Brownian increment comes after that. So it is independent from the stochastic process Xi. So therefore the expectation of X times the delta W is the expectation of X times the expectation of the delta W. And then I am basically done with my proof because the expectation of delta W is equal to 0. And then basically I'm summing over all zeros and this whole summation goes to 0. And again, I can take the limit argument and then I can complete the proof that a stochastic integral always has mean 0, as long as the x's are not looking into the future, so are kind of are taken at the left point of the integral, of the left point of the time step. A second important property is that something which is known as the Ito isometry. That is the variance of a stochastic integral. So that is the expectation of the stochastic integral squared. It turns out is the expectation of the x squared process, but then integrated normally against time. And here you can kind of feel what's happening. We are going to get something like delta W squared is going to turn into a dt. So let's go down to the proof. Is now if, again, I have x has to be taken from the left point, so it still has to be adapted. And I'm going to use independent increments. So if I take the expectation of the sum squared, I'm going to first split the sum squared into a double summation for j is a summation over 0 and a summation over I. And I'm going to take all the pairs of outcomes. So I have xj delta t, xi delta t, then the Brownian increment at j and the Brownian increment at t. And then I'm going to say, if I take an expectation of a summation, that's a summation of an expectation. And then I have these independent increments. And then I am saying, well, if j and I are different from each other, then the one Brownian increment at j and the other Brownian increment at I are independent from each other. Therefore, I can take these two expectations and they will all slam to 0. So only the points on the diagonal where j is equal to I, then I have a Brownian increment squared, but that Brownian increment squared, those terms on the diagonal where j is equal to I, that Brownian increment squared becomes a delta t term, and then I am done. So it's independent increments. That takes all the off-diagonal elements from the summation to 0, and then on the diagonal I have a Brownian increment squared, and the Brownian increment squared is delta t, and then that basically clinches the proof of the itoisometry. So if we have a stochastic integral where we can say the random variable x at time t is an initial value x0 plus an integral from 0 to small t of a possibly stochastic process b of s integrated normally against s, and then another stochastic process sigma s integrated at ws. This is kind of a general form of a stochastic integral. We will most of the time write this integral equation in shorthand form as d of x is b dt plus sigma dw. So we kind of, let's say, take the integrals away and use this differential notation. And the shorthand notation is known as the stochastic differential equation. And it's a little bit tricky, although the d's kind of make it look that this is a differential equation. You always have to remember that a stochastic differential equation does represent stochastic integrals, stochastic Ito integrals, and you are not allowed to manipulate this as ordinary differential equations by, I don't know, dividing by dt left and right. If you start dividing by dt here, then we get dw divided by dt, which is the time derivative of w, and there really things go wrong because, as we saw, the Brownian motion is not differentiable. If I start dividing by dw divided by dt, things really go wrong. So the notation is kind of convenient, but you have to be careful that you always have to remember that this is shorthand notation for stochastic integrals. So it's only the stochastic integrals which are mathematically properly defined. And the differential notation is kind of clever shorthand notation, but the differentials by themselves are not really well defined. Okay, let's take a look at our first example. Suppose we have a stochastic differential equation with constant coefficients. So we say that d of x of t is a dt plus b dw, and a and b are really constants. We do it the proper way. We say, well, yeah, this is a differential equation. It looks like a differential equation, but it is actually an integral equation. So the stochastic process x at time capital T is the initial value x at time 0 plus the integral of the constant a times dt plus the constant b times dw. And when a and b are constants, we can do these integrals. So this is actually a times capital T plus b times the Brownian motion at time capital T. So then it's just a sum of two deterministic variables, x0 plus at, and a random variable, the Brownian motion at time capital T. And therefore the distribution of x capital T, we can basically read this off directly from this definition here, has mean x0 plus at, and the variance is b squared times capital T, which is the variance of the Brownian motion. And we can extend this when we have deterministic functions a of t and b of t. Then the stochastic integral becomes x0 plus the integral over at dt, but this is a deterministic integral, and a bt dw. And then we can use itoisometry to conclude that x of t still has a normal distribution with mean x0 plus the integral over the a of t function. And the variance is by itoisometry the integral over the b squared function dt. The next step that we're going to make is to use Ito's lemma. So this is kind of a way of manipulating stochastic processes and kind of considering functions of stochastic processes. So let's suppose we have a stochastic differential equation where the drift and the variance term are functions of two arguments. So I have a function mu of t and maybe the process x itself, and I have a function sigma that depends on time and the value of the stochastic process. So if I have this stochastic differential equation, if I now introduce a new stochastic process, capital Y, that is another function f that depends on t and x of t, what is then the stochastic differential equation for this new function y, for this new stochastic process y? And can we express this in terms of the function f that we use and the mu and the sigma that we have here? And one way of deriving Ito's lemma is to say, let's consider the process again over a time step delta t. If we consider the process over a time step delta t, we can discretize the process as delta x is this function mu tx times delta t plus sigma tx plus delta w, and this is an approximation, but the error that we are making is of order delta t to the power 3/2. So the Brownian motion increment behaves as square root of delta t. Obviously, delta t behaves as delta t itself. So we have a square root of delta t type of term. We have a delta t type of term. And this approximation is accurate up to order delta t. And the first error term that we make is kind of a square root delta t times delta t, or delta t to the power 3/2. And now what we're going to do is we're going to say, let's do a Taylor expansion for this function f in the t and the x direction. How does this Taylor expansion work? I'm saying, so I'm doing a Taylor expansion in basically 2 dimensions simultaneously. I'm going to say the function has an argument in t and an argument in x. So the function at the end of the time interval at time t plus delta t, but then the x process also has moved from x to x plus delta x. If I have a function in 2 arguments, I can basically expand in the t direction and in the x direction. So I'm saying it is the function where I started at t and x. And then in the time direction, I'm taking a time derivative. So this is the f sub t. And I multiply this with the length of the time step delta t. I'm going to take an x derivative. I'm going to take the x derivative of the function f. And again, I'm going to multiply that with the length of the time step delta x. And the new term that we're going to get with Ito's lemma is that we also need to take the second derivative fxx into account. So this is a second order Taylor expansion in the x direction. So we're going to combine a first order Taylor expansion in the t direction with a second order Taylor expansion in the x direction. And then I'm going to get 1/2 fxx times delta x squared. And you may guess a little bit why we are doing this, because delta x itself still depends on the Brownian motion, but the Brownian motion is of order square root delta t, but we want to collect all the terms up to order delta t, and therefore we need to collect an extra delta x squared term. So delta x was mu delta t plus sigma delta w plus an order delta t 3/2, and delta x squared, if I square all this expression here, well, delta t squared is order smaller than order 3/2, so it goes in the O term. The cross term, mu delta t times delta w, is order delta t to the power 3/2, so I don't need to be worried about that. So the only term that I'm picking up is the sigma squared delta w squared term, which gives me a sigma squared delta t term. And all the other terms are kind of disappearing into the O of delta t 3/2. So now if I take this definition of delta x and this definition of delta x squared and substitute it all here and collect all the terms and bring my f sneakily to the left-hand side of the equality, I get that f at time t plus delta t minus ft is equal to, opening some large parentheses, the time derivative term, the x derivative term, plus the 1/2 fxx squared term. And that, I get this part here, it gets me a sigma squared times delta t. And then I take the Brownian part from this guy here. So I'm getting an f of x sigma times delta w. And then I have my error term of order delta t to the power 3/2. And then again, I'm doing a bit hand waving here. If we now take the limit for delta t going to 0, then I only need to be worried about my order delta t terms and my square root of delta t terms, and these higher order terms are falling to 0 fast enough. So this difference in f is a delta f, which becomes a df. And then this term in square brackets is basically the same, and the delta t becomes a dt, and the delta w becomes a dw. And this answer here with this extra red term, so that I've put this red extra term because this is the extra term you should never forget when you apply Ito's lemma. These first two terms are kind of the natural terms, but this red term is the extra term that arises due to the stochastic square root of delta t type of behavior of the Brownian motion, of the stochastic process. So this form of Ito's lemma is kind of the one-dimensional form of Ito's lemma. So this is theorem 5.1 in the book by Yoshi, and theorem 5.2 gives the generalization to Ito if I have multiple Brownian motions or if I have multiple X process. So if I have a higher dimensional version. Again, the type of proof is exactly the same. I do my Taylor expansion in even higher dimensions, and I only need to pick up one time derivative, but I need to do a second order multivariate Taylor expansion in the X direction. So the notation is a little bit slightly more cumbersome with summations, but hopefully the idea of doing Ito's lemma in higher dimensions is not much more difficult than doing Ito's lemma in a one-dimensional setting. So now with the help of Ito's lemma, we can manipulate, or we can work with a larger class of stochastic processes, or we can find solutions for a larger class of stochastic differential equations. And perhaps the most famous type of stochastic differential equation in finance is the geometric Brownian motion process, which is defined as ds is mu times s dt plus sigma times s dw. So now we do have a stochastic drift and a stochastic diffusion term, because the stochastic process S also appears on the right-hand side in a stochastic differential equation. And what is a trick for solving this geometric Brownian motion is to say, let's consider a new process Y that is the logarithm of S. And I'm now going to apply Ito's lemma with the function f of ts, and I have no time dependence. I only have a dependence in the s direction. So the function f of ts is basically the logarithm of s. So if I apply Ito's lemma, I get that d of f of s is the time derivative plus this drift term mu times s times the s derivative plus 1/2 sigma squared s squared times the fss derivative. And for the logarithm term, I get a very nice cancellation, is that the time derivative is equal to 0 because there is no time dependence. The logarithm of s is 1 over s. So the derivative of the logarithm of s is 1 over s. And the second derivative, or the derivative of 1 over s, this is basically s to the power minus 1. And if I take the derivative of s to the power minus 1, I get minus 1 times s to the power minus 2. And now we see very nicely that this s cancels against this s, and this s squared cancels against this s squared, but we have to take care of the minus 1. And we do get that the y process is a stochastic process with constant coefficients, but with one coefficient mu minus 1/2 sigma squared and another coefficient sigma. So now we have a constant coefficient solution, and we can go back 2 or 3 slides, and we know that the y process has now for each time increment t a normal distribution with mean mu minus 1/2 sigma squared times t, and variance sigma squared times t. So the solution of the geometric Brownian motion is the initial value as 0 times e to the power of the y process, and the y process has mean mu minus 1/2 sigma squared t, and variance, it's the solution of this guy here, it's sigma times the Brownian motion at time capital T. And if I take the expected value of s of t, then you may be worried about this minus 1/2 sigma squared, but the minus 1/2 sigma squared as a deterministic term comes outside of the expectation. But because the Brownian motion itself is stochastic, I get a Jensen's inequality term, and this gives me a plus 1/2 sigma squared, and that very nicely cancels against this minus 1/2 sigma squared. So the expected value of the Brownian motion is the growth rate mu, and that is this growth rate here. In fact, you are allowed to say, I take the expectation on the left-hand side and the expectation on the right-hand side, and then you say, well, expectation against dw is equal to 0, so this term disappears, and the expectation of s solves the ordinary differential equation. The expectation of s is mu times the expectation of s dt, and that indeed has a solution of exponential growth with growth rate mu. Now the last step, and this is of course, let's say a very famous application of Ito's lemma, is of course the derivation of the Black-Scholes option pricing formula. And in fact, the Black-Scholes option pricing formula with continuous time processes. So in week 1, we talked about the binomial tree, and we made this kind of discrete time steps. And then in the case that you worked out, you had to take the limit for a larger and larger and larger amount of time steps. And then you see this binomial tree process kind of converging to the correct value. Here we are going to compute directly a closed form expression for this limiting value from the binomial tree economy. So what do we want to do is we want to look at the price of a call option, capital C, and this call option is a call option on a stock ST with expiry date capital T and with strike K. And the payoff of a call option then is the maximum of ST minus K, 0. And for the stock price process, we're going to use this geometric Brownian motion model. So ds is mu s dt plus sigma s dw. And I'm going to say that I have a risk-free constant rate of interest R. So any money that I put on my bank account is with continuous compounding, growing exponentially with an ordinary differential equation, dB is RB dt. And in my derivation of the option pricing formula, I'm going to assume that the option price at time small t is a function C of small t and the stock price at time small t. And you may guess where this is going. We have a function C of t and s follows the stochastic process. So we can derive the stochastic differential equation for the call option price process, and we can apply Ito's lemma to that. So we get that d capital C is the time derivative of C plus the s derivative of C plus 1/2 the second derivative in the s direction, and that's all the drift term. And then we're going to get the C as sigma s dwt. And the notation is slightly confusing, but hopefully it's not too confusing. So s sub t, then t is just a time index, but in this function capital C, the sub t actually means the partial derivative with respect to time. Yoshi does this nicer by doing these partial derivative symbols, but then let's say the formulas get a little bit messy. So I kind of like to use this subscript notation with the slight price that I'm paying, that s sub t is just a time index, but here the sub t is the time derivative. So I hope you forgive this slight awkward notation here. So we have derived the stochastic differential equation for the C process, for the call option price process. Now we're going to say, let's consider a portfolio where we have C. We have one call option, and we're going to add alpha times the stock price at time t. Then if I apply Ito's lemma again, this is a new function of time and s. Well, then the s derivative of alpha is very simple. It's linear only, but it has no quadratic term. So I'm basically getting almost the same expression as on the previous slide, but the first derivative becomes cs plus alpha, and I have a cs plus alpha here, but the time derivative and the second derivative remain unchanged. And now we're going to make a clever choice, and this is exactly the argument that Black and Scholes originally made, is by saying, if I choose for alpha minus this first derivative, then something magical happens, because the cs, the plus cs and the minus cs cancel here against each other, and they also cancel here. So then the differential of c plus alpha star times the stock becomes a time derivative and the second derivative and a zero dw term. Now, if you are very sharp, you are saying, well, wait a minute, when we did the derivation here, we pretended that alpha was a constant or alpha was a parameter. But here we are making alpha a stochastic process. So shouldn't we be applying Ito's lemma on the alpha star process itself? The answer is, in theory, we should, but it turns out that if you make an additional assumption, or if you include an additional assumption that my gains from trading only come from buying at the beginning of the interval and then picking up this differential, again, this kind of left point type of argument, this is known as a self-financing condition of my hedging portfolio. It turns out that very conveniently, all these extra Ito's lemma terms cancel away, and this kind of simple type of derivation is actually the correct answer. So Mark Yoshi spends a bit more time on this in the book in chapter 5. But let's say this is kind of the basic argument, and this is what Black and Scholes originally did. And I think Black and Scholes kind of overlooked this stochastic argument, but they by accident ended up with the correct answer. So if you make this argument here and you say, well, now I have a zero dw term here, so this thing is now locally risk-free. There is no risk because there is a zero dw term. But if I have a portfolio that is locally, for a very small time step, risk-free, it should behave like the bank account. So it should behave as if I have put C plus alpha star times S on the bank account. And how much money do I earn on that? Well, I earn the risk-free rate R times dt. So this dt increment here should be equal to R times C minus the first derivative of C in the S direction times S times dt. And if I now divide by dt on the left and the right hand side, and if I switch some terms around, I am getting a partial differential equation where the time derivative of C plus R times S times the first derivative in the S direction plus 1/2 sigma squared S squared times the second derivative in the S direction of C minus R times C should be equal to 0. And this is a partial differential equation, a PDE, and I know that the boundary condition at time capital T is equal to the payoff. So we now need to solve this partial differential equation. And this is actually not so easy to solve this kind of from first principles or kind of by direct attack. And in fact, it was the case that Black and Scholes derived this partial differential equation a few years before they eventually published their paper. So they used basically this type of argument, derive that partial differential equation. Then they basically got stuck because they didn't know how to solve this partial differential equation. And this paper was kind of sitting there. They have a very complicated partial differential equation, but no explicit solution. And then a young PhD student, Bob Merton, came along and he said, oh, but wait a minute, I know how to play with partial differential equations. I can actually solve this partial differential equation for you. And the way to manipulate this partial differential equation, also Mark Yoshi shows this in his book, is again to first kind of do this log transform. So to consider a new variable z, which is the logarithm of s, and to say, well, this minus RCT, if you know partial differential equations, to say, well, this looks like a discounting term. So I'm going to introduce a new function, small c of small t and small z. That is e to the power plus RT times the capital C function evaluated in the t argument and in the e to the z argument. If I substitute this relation into the partial differential equation, all kind of terms cancel. Like what we saw, the log transform basically cancels the s dependence here, but you get an r minus 1/2 sigma squared. And this term here kind of cancels the r of c. So I'm left with this partial differential equation here, which is a little bit nicer, but still quite daunting. But we only have constant coefficients here. So there are no z's sitting here and here anymore. And a partial differential equation, which is linear in time and has a first and a second derivative in the z direction with constant coefficients, is a type of partial differential equation that physicists know very well. And they know this as the heat equation. And how do you solve the heat equation? Is that you guess a solution, a very specific solution, which is known as a fundamental solution. And the solution looks pretty complicated. So the partial differential equation is a function in small t and small z. So I'm going to introduce a function phi, which is a function of small t and small z, which are kind of in orange here. But I'm going to introduce two auxiliary parameters, capital T and capital Z. And the functional form of the phi is this kind of normal distribution. If you see it for the first time, you see a lot of symbols here, but you see kind of a capital Z minus a small c and a drift term. I'm dividing, and then I'm taking the square, e to the power minus 1/2, and I'm dividing by sigma squared t minus t, and I take the square root of 2 pi sigma squared t minus t. So this is like a normal probability density function. But the variables that you want to solve for, the small t and small z, I've kind of made orange here. So these are the variables that when you are substituting phi into this partial differential equation, you are taking derivatives in the small t and the small z direction. And it's a bit messy, but if you substitute this function phi and evaluate all the derivatives and substitute it in here, all these terms, all these partial derivatives will cancel out. So this phi is a solution to the partial differential equation. But the clever bit is, it is a solution for every possible choice of these extra parameters, capital T and capital Z. And this special type of solution is called a fundamental solution. And why is this fundamental solution very useful? Well, if I have for one choice of T and Z a function phi, that solves the partial differential equation. If I choose another numerical value for T and Z, that phi with the other parameters also solves this partial differential equation. And because the partial differential equation is kind of linear in the derivatives, if I add a phi1 with the choice of T1 and Z1, and if I add another phi2 with another choice of capital T and capital Z, T2 and Z2, then the sum of the phi1 and the phi2 also solves the partial differential equation. So I can kind of take linear combinations, or I can add sums of these phi's in the capital Z and capital T direction. And if I take a sum of all these phi's, then that still is a solution to the partial differential equation. With phi, small t, z, capital T, capital Z, you can recognize this as the probability density function of a random variable capital Z that has a normal distribution with mean Z plus R minus 1/2 sigma squared T minus T and variance sigma squared T minus T. And this mean and this variance, you kind of see them sitting here. This is the drift term. This is the variance term. You see, this is all quite closely related to Ito's lemma, and we're going to show more of this connection in next week. And if we let small t approach capital T, something special happens, because then the variance of this normal distribution, if small t approaches capital T, this normal distribution collapses into a deterministic thing. And we denote this by a Dirac delta function. And now we have, let's say, how do you solve a partial differential equation with the help of this fundamental solution phi? By saying, if I now have a payoff at the end, maximum of st minus k and 0, then I can do the following trick. The price of the option is a function of small t and small z, denoted in orange here. And that is the small t and small z sitting here. But now I'm going to say, I'm going to take a linear combination of all those phi solutions for different values of capital Z. And how am I going to mix those values capital Z together? Well, each value of capital C, I can see as a realization of this random variable Z at time capital T. And the payoff, the stock price at time capital T, is e to the power Z. So if I substitute the payoff function, the discounted or the undiscounted payoff function, e to the power RT times the max of e to the power Z minus K, and I integrate the fundamental solution over all values of Z, so that's why I've made these Z values red, I am taking a linear combination of all these fundamental solutions. And then in the small t, small z direction, they do solve the partial differential equation. And by doing this integral choice, I also solve the boundary condition, payoff boundary condition at time capital T. So that's why this trick with fundamental solutions is very clever and very useful. So the solution that I have for the option price is of the form, I take an integral over a payoff over a random variable capital Z, and I multiply that payoff with the probability density function. But integrating a random variable against its probability density function is taking an expectation. So this integral I can also write as taking the expectation of the capital Z random variable, but then I have to realize that this capital Z random variable has this normal distribution here. And it turns out, it's a bit messy, but it turns out that you can actually explicitly compute the solution of this integral. It's a bit nasty. And then the explicit formula that comes out of that integral is the Black and Scholes formula, the very famous Black and Scholes formula. And Yoshi in chapter 5.9 or in section 5.9 shows you how to do this Black and Scholes formula. Now with the fundamental solution trick, using this particular payoff is basically not something very special. This fundamental solution trick works for any payoff. So if you know a function f at time capital T of the random variable Z, then you can price any option with any payoff as basically applying this fundamental solution integral. So integrate over all values of phi and then integrate over the capital Z for the payoff function f of capital Z. I'm going to show one last thing, but is a little bit outside of what Yoshi does in the book. And I'm going to show you a connection between stochastic integration and the binomial tree. So we go back to the Brownian motion as a random walk. And I said the Brownian motion, I can write this as a coin flip by going either up with a plus square root of delta t or going down with a minus square root of delta t. And I've now made a non-recombining binomial tree. So if I take 1, 2, 3, 4 time steps, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possible outcomes at the end. And 16 you may recognize as 2 to the power 4. I'm going from 1 step, that's 2 to the power 0, to 2 steps, to 4 steps, to 8 steps, to 16 steps. And in this 4-step non-recombining binomial tree, I can basically say any possible stochastic integral I can represent as z integrated against the Brownian motion dw, but the z random variable on a 4-step binomial tree, but evaluated at the left point. So I can, if I do a stochastic integration, I take the z at the beginning of the interval and I multiply that with the change of Brownian motion during, let's say, the time step from the beginning of the interval to the end of the interval. So there are 15 z values at time 0, at time 1, at time 2, at time 3. So there are 15 z values that I can use to define my stochastic integral. And I have 16 possible outcomes. So the random variable capital I has 16 possible values, which are a function of the z process that I encounter along the way. So if I go up along this path, so I at 1, 1, 1, 1, which means the path that went up, 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 up. What's the value of that stochastic integral here? Well, I start with the z 0, and then I do a plus square root delta t, and then I encounter z1 with another plus square root delta t, and then I encounter z11 with another plus square root delta t, and then I encounter z111 with another plus square root delta t. So I get the plus z0 plus the z1 plus the z11 plus the z111, and all multiplied by square root delta t. If I look at this path here, I went up, up, down, down. So that's the 1, 1, 0, 0 notation. Then I have the z0 with an up move, the z1 with an up move, but then the z11 with a down move, and the z110 with a down move. So I get plus z0 plus z1 minus z11 minus z110, and all multiplied by square root delta t. So you see that I get 16 values that depend on basically a subset of 4 of the 15 z values that I encounter along the way. Why do I do this construction here? Because we can basically go in 2 directions, and this is something that is mathematically known as the martingale representation theorem. But most of the finance textbook and also the book by Yoshi are a bit vague on that. So they're kind of saying, well, the martingale representation theorem exists, but we are not giving a proof here. And I want to show that at least in this binomial tree setting, you can quite explicitly see that you can go in 2 directions. So if I have a 4-step tree, then I have 15 degrees of freedom for my z process. So I have 15 possible choices for my z process. And it looks like that I have 16 possible choices for my I process. But it's very easy to see because I has to be a stochastic integral. The expected value of I must be equal to 0. If you would work this out with all the probabilities, you can actually show that this random variable I always must have an expectation equal to 0. So it looks like that I have 16 possible values or 16 degrees of freedom, but I remove 1 degree of freedom because the expectation must be equal to 0. And then we have this very nice connection that I have 15 possible values for my I process and 15 possible values for my z process. And that kind of shows in the binomial tree that we can go in both directions. If you give me a z process, then I know how to construct the I. This is kind of the normal way of going forward with stochastic integration. But you can also go the other way around. If you give me a capital I random variable with expectation equal to 0, so then there are 15 degrees of freedom, then these 15 values of I uniquely correspond to a t to a z process. And this backward way of starting with the random variable capital I and then kind of backing out what the z process is that I need to integrate, this is known as the martingale representation theorem. And in the binomial tree, you can kind of see what we are doing. Suppose I want to find out what the z111 is. Well, the z111 influences the I 1111 and the I 1110. If I compare those two values, I see that they both have the same plus Z0, both the same Z1, both the same Z11. The only difference is between I 1111 and 1110 is that the last value is plus Z or minus Z. So if I take this value of I for the up state and I subtract the value of I for the down state, then all the other Z's cancel and I get something like 2 times the Z111 times square root delta T. So the Z111 value I can kind of reconstruct by taking the difference between I for the up move minus the I for the down move divided by 2 times square root delta T. If you say, wait a minute, this looks a little bit familiar because this was kind of almost the same that we did for the binomial tree, how to construct a replicating portfolio. I took the F, the payoff in the up state minus the payoff in the down state, divided by the difference in the stock price between the up and the down state. We are basically doing the same thing here. We are taking the value of the random variable in the up state minus the value of the I random variable in the down state, divided by the distance between the Brownian motion in the up state and the Brownian motion in the down state. And that is 2 times, it's plus square root delta T minus square root delta T, and that is 2 square root delta T. So actually what the binomial tree does in constructing the replicating portfolio is very closely related and is actually the same thing as the martingale representation theorem. So what you are doing in a binomial tree is deeply connected to, let's say, the martingale representation theorem, and basically going backward by saying, if you give me a payoff that I want to replicate, there is a unique trading strategy, which are these kind of DZs, that is the replicating portfolio that replicates that particular payoff. Yeah, so this is a little bit of extra information that is not covered too well in the book by Yoshi, but I think it's especially in the binomial tree setting, I think it's very insightful to have this explicit insight that we have this two-way street. You can start with the Z process and then construct the stochastic integral I. But you can go the other way around by saying, if you give me a random variable I that has expectation equal to 0, then I have sufficient information to kind of uniquely determine what magical choice of the Z process I should take to recreate the stochastic integral that gives me an I process in each state of the world. That's it, and I'm going to stop the presentation or stop the recording now.